So now I'm gonna move to the topic how you can just okay. How we can use both CUDA and OpenACC in the same code. So there are basically two parts into this. One is, can I use a CUDA pointer inside OpenACC context? And the second part is, can I call a CUDA function from an OpenACC context? So it's two different scenarios that they are treated differently. And the short answer is yes. So now I'm going to show you how the different scenarios and how this can be achieved. So let's get the first scenario, which is use CUDA pointers inside OpenACC. So the scenario could be, I have a CUDA code that needs to call another library or something that's implemented in OpenACC and requires, for some reason, a device pointer. So this function gets an array that has been allocated already on the GPU, but this allocation has been done by CUDA. So the problem is that OpenACC, with what we have presented until now, doesn't know about this array, this pointer. So it's not in its, because OpenACC does a bookkeeping of the data structures it allocates and the pointer, so that it knows what is on the device, what's on host, and there should be a mapping. So suddenly you give it a pointer, and if you just try to put that this pointer is present, then you will get an error, a runtime error that I cannot find this pointer in my present table because I didn't allocate it and I don't know about it. So there is a solution to this, and the way to do it is to instruct basically the OpenACC runtime to somehow trust this pointer, that I know this pointer, it's a device pointer, just take it and go ahead as if you had allocated. And the directive to do this is, basically it's not a directive, it's a clause, because device PTR that gets a pointer list. And it can be used with parallel kernels and the data directives. So in your parallel loop, you just say that the following pointer I'm using, device PTR, is a device pointer, and just go ahead and use it. So this is an example. For example, I have here a silly function that just copies something, and it does that as a parallel loop. And then here I'm just using CUDA to allocate the data on the device. And then I'm calling that function. And this function I cannot put present here because OpenACC runtime doesn't know about DST and SRC because they have not been allocated by OpenACC. So we just have to tell that these are device pointers, and that's it. We have hands-on on that so that you can also practice. Okay, next thing. So the next thing, which is even a more common scenario, I would say, is when you want to call a library function that is written in CUDA, and you want to call it from OpenACC. That's a common scenario because, first of all, you have the cuBLAS methods, which are quite optimized methods for standard BLAS operations. And these are written in CUDA, and they accept, in their interface, they accept device pointers. So you have to pass them a pointer that you should have done your allocations, etc., and pass it to the function. Another scenario is I write my code in OpenACC, but I have a kernel that I just want to optimize this to CUDA because for whatever reason I'm not getting the maximum performance, and it's quite performance critical for me. So I just write it to CUDA, but I need a CUDA pointer. So to achieve this, the problem is that comes to what we have discussed a bit before about this, that a variable in an OpenACC program can either refer to device copy of the variable or the device pointer of the variable if it's an array, or to the host. But the thing is, this is only happening inside parallel or kernel's region. So you are already executing and then you see the device copy. But here you need to see it outside this. But currently outside this, the only thing you see, the only thing an OpenACC program sees is just the host pointer. So ideally, you would need to have a way to ask the OpenACC and tell it the runtime and tell it, okay, give me the corresponding device pointer for this data structure. And the solution is there is a special directive called host data, and you say host data use device, and here you put a variable list. Let's see it a bit more in detail. So you say ACC host data use device takes a variable list. So in the next block of code, the variables that they are here in the variable list, in the next block of code, you will, whenever you reference them, you will actually be getting the device pointer. And similarly here, since it's a block of code, you need to put end host data for Fortran code. It also has some optional clauses. I think these are additions of 2.6 of the latest standard. Am I right? Yes. So you can add a condition here. So if a pragma-ACC host data use device if condition, so it's then only if the condition is true, then only then use the device pointer. And this has come up because people wanted to support easily both versions, both a host and the GPU version, if a condition was true. And then it's if present is if the pointers here in the var list, the variables here are present on the device, then just only then use the GPU version. Otherwise, just use the host pointers. We will see again this directive and why it is important. So any questions so far? It's not something strange. Okay, so I can move on then to a bit more advanced topic. So interoperability with MPI. I guess lots of you are going to use OpenACC or have been using it with MPI. So what is the data path when you have an OpenACC program that you have a node basically that you have your network card here, you have your GPU, there you have your array, here is your MPI library, and you have copied in your array in the GPU and you're doing some work here. And then you want to send basically this array that you have computed, communicate it to another node. So what's going to happen? What would you do? Any ideas? How you would do that? I mean, what's the natural way of doing it?
Transfer data from GPU to CPU
and then call the MPI to do the transfer. Yes, that's correct. So that's the way to do it. And let's see what's happening. So first we need to do an update host to update our data copy. Okay? And then we call an MPI send. So this will MPI will copy the buffer to send, and then MPI will send it to the next node. Here, I'm assuming also an optimization, because this is not the fully unoptimized path. Because the fully unoptimized path, then the kernel would have to copy this to a pinned area so that then the network card can access it and move it to the network. This is a bit optimized path, assuming that MPI implementation supports what's called RDMA. So basically, it pins this buffer here so that then the kernel can directly instruct the network card to pick the data from here and put it directly to the network. It saves one copy. But so far, we have done 1 copy, 2 copies, and then essentially 3 copies to get to the other end. And then on the other end, again, we have the same thing. So from the NIC card, from the network card, we go to the MPI receive buffer, to our user space, and then update the device to get it on the GPU. So that's like 6 copies. So this, if you have frequent communication, that's not very, very efficient, okay? Thankfully, there is, so as I said, there are too many copies. And as I said, I'm also assuming 1 copy has gone out, or basically 2 copies. So ideally, what we would like, we'd like to avoid these copies. So we'd like, I mean, since we have our data already in the GPU, ideally, we'd like to communicate this data in a magic way to the other GPU, if that's possible. So just bypass everything. And thankfully, there is the technology for that. This is called GPU Direct, which is also from the CUDA driver supported and from the hardware of the cards. And also, you should have a high-end network card as well. So let's see what's happening. So ideally, yes, and this is happening. So when you do an MPI send, and if you instruct the MPI library that, okay, send this buffer, and the API implementation sees that this buffer resides on the GPU, then it can set up directly a DMA from the GPU to the network card. And then we avoid all the copies, go to the network card, and then again to the GPU. So to avoid all this complex data path, and everything happens inside the kernel. So this is really beneficial in terms of performance. Now, but it's not always that you have it available. So first of all, you need the MPI implementation must support it. And thankfully, our Cray here at Pittstain, we have the Cray MPI CH implementation, which does support it. We just have to enable it. And then the second thing is you have to, in order to enable this data path, you have to pass a GPU pointer to the MPI calls. And in order to achieve that, we just seen the directive to do that, which was the host data, basically, directive. So you have your OpenACC data on the device, and then instead of just doing an update to get it back, and then just use normal MPI calls, you just wrap the MPI calls in a host data use device, and you pass basically the arrays. So this way you just pass the pointers to the send and receive calls, and then you enable this path. And we're going to see it in the hands-on sessions how this can be, how beneficial can this be. So any questions on that? Yes.
So for Fortran, is the same thing or is different?
Yes, you can still do the same thing in Fortran. Okay. So yes, these things are more practical. So if you don't have any questions, then I don't know, we can move to presenting the deep copy, and then from next session we can start with a hands-on. Yes, please. Yes. Yeah, but we still have some time for that.
When you have RDMA enabled, MPI will still continue to behave the original way if you don't use CUDA pointers, right? You can still use MPI from the CPUs, copy CPUs to CPU.
Yes, but you mean the default optimization where it just bypasses the what do you mean?
I mean, you don't use the CUDA pointers for some reason. There is a piece of code that needs to use MPI just from the CPU to another CPU.
Yes, that's exactly. I mean, it's still the classical way. It's still there. If you pass a CPU pointer to send receive calls, then it will do just as what it used to do. You just make it recognize GPU pointers and enable this path. Okay.
Yeah, so just a question. So in case if, for example, if a cluster, you have here this technology, if in some other cluster, if there is, they don't have this technology, then how would this host data, pointer device would work? Would it work in such clusters, or you have to
no, if you
modify
do
your
that, then
directive?
probably it will crash,
Yeah.
because then the MPI implementation will just you can see it even in our exams if you don't set this variable, because this is what enables the feature. You will see that it crashes, and if you use host data use device, then it will crash. So in that case, you'll have to do the update, and then first update host, then update device. So it's just an additional feature. So I can, since we still have some time for the break, I'm just gonna go through quickly what are the related, the exams we're gonna, the hands-on we're gonna do. I have one example is we're gonna call kublas from OpenACC, but this has also two sub exercises. One is there are two kernels. One kernel is just the naive one. It's just the matrix multiplications just out of the math textbook, which is unoptimized. Do you know why? Does anybody know what this is quite unoptimized? If you just try to implement directly matrix multiplication with this three-way nested loop, and you just do at the inner loop CIK equals AIK by BKJ. What you see in the equation of computing matrix. Yes.
Actually, I don't really know. It's just a guess. Maybe because one of the array has to be, you have to index it with the non-contiguous indices.
Yes,
one of the two.
Yeah, it's just like that. So the problem is that your tight loop, your internal tight loop, in the axis of the second array, you're doing, for example, BKJ, and if you assume that you have row major order, or for the A array, if you have column major order, then your tight internal loop, you're always jumping complete lines in the memory. And this is really bad for performance, for cache performance. And it's also really bad also on the CPUs, but also on the GPUs. And since we're talking about that, why? Okay, on the CPUs, it's because you don't have cache locality. But can somebody of you imagine from what we have said yesterday, what is the problem on the GPU? What is the key problem there? I mean, again, it's related to that, but you don't have like large caches that you could say it's the cache that, in any case, it won't fit. But what is there the problem?
So you have to go from the gang level to the thread level. So you have to go from gang level to thread level because your data is not fitting in just one line of thread or vector. So
the parallelization is still the same. Again, you're at the vector level, so every vector does the computation. But the thing is, what are adjacent threads in the warp do in such case? What is the access pattern? So I assume the inner loop, and then thread I, what it gets, I mean, it computes the IK, and then the adjacent thread for the next element, it gets the KJ. And then the next access you do, the thread after you, does another access which is further away. So you have, the pattern is that you have, I mean, imagine your 32 threads of the warp, and then the first thread does an access here, the next thread does another access 1,000 elements apart, the threads adjacent to you 1,000 elements apart, if you have a 1K by 1K array. And this is really detrimental for performance, because this is what, if you remember, I have mentioned in the introductory slides, the memory coalescing. So if the threads of a warp access adjacent locations in memory, then then all the data they need, all the 32 threads, will be brought with 1 or 2 transactions from memory. Whereas if you just jump like that, so the thread 1 just gets location 0, the next thread gets location 1,000, then you will have, for example, 32 transactions for memory access, whereas you could have just 2. So your performance will drop by a factor of 16. So that's why also this approach is very detrimental in terms of performance on the GPU. So this is the first version of the OpenACC kernel you're going to do, just to see how slow it is. Then we have a flag that to disable it, and by default it's disabled because you cannot have large arrays. Now, then we have a second optimization, but we don't ask you to do it. It's there, the optimization. You just need to put the directives. And can anybody imagine what is the standard optimization, the number one optimization that somebody must do in a matrix-matrix multiplication kernel?
You transpose one of the two matrices.
Yes.
Well, when you launch the data, you launch the transposed. When you put the data in the GPU memory.
Okay, during the transfer, you do also the transpose, but also the transpose operation is not very. It's not very friendly in terms of memory bandwidth as well. But it's easier the solution than that. Does anybody have an idea? So the standard optimization is loop reordering. So you just reorder the loops, and so that your internal loop has contiguous accesses. So you move the jumps outside, and your tight loop internally, it just has regular accesses. The downside of that is that understanding the algorithm and how are the accesses and how you finally compute the matrix-matrix product, you have to go with pencil and paper to see what are the actual accesses and how you do the additions. But it's just an optimization just like that, swap two loops. and then you will see that the performance is really good. Then you have a decent matrix kernel. And the next level of optimization, what it is, when you have, a matrix kernel. Then the next standard optimization before diving into architectural details. What is the difference of a matrix kernel versus a matrix vector kernel in terms of performance characteristics? Both of them are independent in the sense that they are embarrassingly parallel, in the sense that both of them are, you don't have any dependence between the different. They're quite parallel as well. So, what is, I can rephrase the question. So, we have still some time until the break, but I think it's interesting. So let's get the other way. The matrix vector kernel. So you have a matrix, and for each line of the matrix, you multiply it with a column. How many times do you go over the elements of the matrix in a matrix vector kernel? Once. You just sweep once through the array, and you compute, you have your product. And so what does this mean? So this means that you have to load the matrix and do the computation. So you have like a constant rate of memory accesses versus computation. So this leads to a very low, what we call flop per byte ratio. That is, we have, you have to transfer lots of data to just do 2 operations. You have to fetch one float, the array element, and the vector elements, 3 floats, just do 2 operations. So you end up having, in total, very low compute intensity. So that makes the kernel, what does it make it, the matrix vector kernel? From what are you bound architecturally? The memory. So the memory bandwidth. So the matrix vector kernel is always is memory bandwidth bound, cannot be something else. And similarly, all other kernels that you just sweep once through the elements is a typical streaming kernel exam. Now, matrix. The matrix, how many operations do you do on the elements of the matrix? Do you remember the loop? How it is? It's a nested, a 3 times nested loop. So how many operations do you do? It's So
well, actually not the non-common dimension of what's the number of
lines or columns, depending on which side.
Yes, but in order of magnitude, if your array is, the array's dimension is n by n, then how many operations are you doing? Huh? N? In cube. N cube. Okay. But how total data you have to bring in total, ideally? You do n cube operations, and then in what order of magnitude is your data that you have to bring basically in the processor to do your n square. So you have a very high compute intensity. So there is lots of potential in this kernel. And that's why it's the kernel that is used to basically burn the CPUs or the GPUs and get the maximum performance. It has lots of potential because it's very, very compute intensive. However, even if you do the loop reordering, you don't get even close to the maximum performance. So what is the reason for that? Any ideas?
I believe that the reason is because either the reads or the writes to the matrix aren't linearized. So if I change the loop ordering, then my writes are not in a linear fashion. And I think the answer you are looking for is some kind of blocking technique. So
yes,
you have to know it.
that's where I'm gonna finish. Well, not exactly where I'm gonna finish, but it's my next thing. Sorry for that. Just let me mute that. Okay. So even if you have optimized the tight loop, the inner one, and you have nice access, then you have other loops outside that they still the access is not ideal. So again, you have cache misses. So again, you have not ideal access pattern. So the next technique for that, but you have potential. It's not that you don't have. So the next thing you do in such a kernel is, in matrix kernel on similar kernels, is what we call blocking. Blocking means that instead of going all over the lines up to the end of the matrix, you split the matrix in small tiles, and then you go compute matrix there, and then to the next, and so on and so forth. And this is very, very efficient because you can have your working set just to fit in your cache, or in the GPU, in an optimized implementation, this would land into the shared memory. So you could have the shared memory. Do you remember? Who remembers what is the shared memory? Just to do a recap, to see if you remember a bit of what we've said yesterday. What is the shared memory in the GPU?
It's a memory between parts.
Hmm?
Is a memory between warps, so which is shared between warps, or?
Yes, within warps, yes, but I would say blocks. So, and where does it reside on the hardware? It's, if you remember the figure I've shown you, we had this multiprocessor, symmetric multiprocessor, where the different blocks, gangs, or whatever we call them, were scheduled, and there was this small memory called shared memory that could also be used as level 1 cache. And it's very, very efficient if you access it correctly. It's just a single cycle latency. So now we've talked about two optimizations. That's whoever has tried to implement them, can be a bit mind-boggling because if you have a 3-nested loop and you just want to apply blocking, how many nested loops would you have? Has anybody any ideas? So you have your kernel.
6.
Yes, 6 or 5. 5, I would say. 5.
Yeah. Okay, last block.
So you have, if you want to implement a blocking on matrix 1, you have 5 nested loops because you will need 2 loops to go over the blocks and then 3 loops to get matrix there. So the implementation gets a bit tough. Then you have on the GPUs, and we're talking about the GPUs, that's not enough even because you want to move this data, this little block, into your shared memory. So you need to move this there and then make sure that the access are ideal so that you can have peak performance. Another optimization, lots of code. That's why we have the libraries. Somebody has written it for us, and we just use it. Or, I mean, you may have written it once just for fun, and you don't want to rewrite it, you just want to use it. So this is the exercise. So we will start with the naive kernel, then the optimization we can easily do with the loop reordering, and then we're going to call kublas, and then we start increasing the size to see from which point on it is worth to to use that one. Okay, so we did also a crash course in performance optimization. So now it's coffee break, and then we can move on.